If you think about our batteries that we've looked at so far, what we've focused primarily on are standard cells. We've talked about E0 cell, we were just looking at delta G0, we're looking at K. However, most electrochemical cells operate under non-standard conditions as opposed to standard conditions, and this is due to two factors, primarily concentrations and temperature. Concentrations especially, because if you can imagine that you have a reaction where everything is at 1 molar, as soon as that reaction starts and you have reactants being used up and products being produced, your concentrations have changed immediately and you are no longer under standard conditions. And of course, we can imagine that temperature could change for various cells depending on their application. Now we have an equation, though, that can take the voltage from a standard cell and use a different temperature and a different set of concentrations to calculate a new voltage based on an adjustment from the temperature and the new concentrations. So those new concentrations basically form a value of Q. And what we're doing is determining how far away is the voltage from that of a standard cell. So we take the voltage of a standard cell and then basically apply a correction based on temperature and concentration. And so here's old Dr. Nernst there, very unassuming looking man, came up with a very brilliant equation there. So we have E cell, so notice that we do not have our little zero symbol there. So that's our E cell under non-standard conditions is equal to the value of E0 cell, so it's our E cell under standard conditions minus a correction factor. And the correction factor is RT over NF natural log of Q. And that Q is exactly what we saw earlier in the course. It's equal to products over reactants. And you do have to remember to look at the balance of the reaction and apply those balancing coefficients as exponents in your Q equation. So you can't forget to do that. Our R is still joules per Kelvin mole. Our temperature is in Kelvin. Our N is still the number of electrons transferred in the balanced reaction, and F is that Faraday constant there. Now again, if we happen to be at changing concentrations but still at 298 Kelvin, then this value here, this RT over F, becomes a constant, and so we can write that if we are still at 298 K. So we've got a couple of different forms. We've got the natural log or the log forms at 298 Kelvin. Okay, so at 298 Kelvin, our natural log form would be E cell is equal to E0 cell minus 0.0257 over N, natural log of Q, or we have the common log one there as well, the base 10 log. So just like before, these are the same equations. It doesn't matter which one you use. Just pick the one you like the best and always use that one. There is no situation where one is correct and the other one is not. But again, just like before, that 0.0257 and 0.0592 are slightly rounded values. And so there are times when the numbers that you come up with for E cell might be off by a digit or two. So let's take a look at an example here. If we look at a nickel aluminum battery with aluminum at 0.001 and nickel 2 plus at 0.5, we can see those are not 1 molar, so we know that we're not under standard conditions. If we're not given a temperature, we can assume that we are at 298 Kelvin. So if we happen to have a table of potentials, we would see that nickel has a higher reduction potential on the table, so that gets the electrons, so it'll be reduced, and it will be the cathode, and so we can write our equation here. We have nickel 2 plus 2 electrons goes to nickel. It has an E0 of negative 0.25. The anode will be aluminum going to aluminum 3 plus 3 electrons. Now, even though we've written that as an oxidation, this value here is still the reduction potential, and that's fine because we're going to use E cathode minus E anode, and when we use cathode minus anode, we do have to use reduction potentials. So in order to add these two equations together, we have to add them so that the electrons balance out, just like before. I've got 3 electrons for the aluminum. I've got 2 electrons for the nickel. So I have to multiply my cathode equation by 2 to get 6 electrons. I have to multiply the anode equation by 2 to get 6 electrons. We add those together and we get 2 aluminum plus 3 nickel 2 plus goes to 3 nickel plus 2 aluminum 3 plus. Okay, notice, very important, that the E zeros do not get multiplied. It is an intensive property, E0, so it does not get multiplied. We have minus 0.25 minus a negative 1.66, and that gives us a positive 1.41. Okay, now how do we use that equation with the Nernst equation? We know that E0 cell is 1.41 volts because we just calculated that. We know that N is equal to 6 because that was how many electrons I had to use for my lowest common multiple to get them to cancel out. Okay, so now the Q, if we look at that previous equation, I'm not going to be able to do it here, but Q is going to be equal to products over reactants. We leave solids out, so the aluminum metal gets left out, the nickel metal gets left out. However, we have those aqueous solutions. So we have a concentration of aluminum 3 plus. That gets squared because it has a 2 coefficient. The concentration of nickel 2 plus gets cubed because that has a 3 coefficient. We put all of that into our Nernst equation here. So we have 1.41, that's my E0 cell, minus 0.0257, that's the constant value of RT over F, over 6, that's my N value, times the natural log of 0.0010 squared, that's my aluminum concentration, over 0.5 cubed, that's my nickel concentration. Okay, we take care of my divising here. My divising here, we take the natural log of 8 times 10 to the minus 6, multiply that by 0.00428, subtract that value from 1.41, and we see that the voltage actually went up, and that is possible. Okay, it's possible to get a slightly higher voltage if you take a battery farther away from equilibrium than it is under standard conditions, or you can have a lower voltage if your conditions put it closer to equilibrium than the standard conditions. So it can go either way. It just depends on the values of your concentrations. So speaking of concentrations, we can have galvanic reactions that occur even when the metals are the same. Now this is a strange, kind of a strange event, but it is really cool, which is why I like to show it in this class. So when the metals are the same, we have no difference in potential energy because the metals are the same. So the driving force to make electrons move comes strictly from a difference in concentration. So electrons will always flow from the half cell with a lower metal concentration to the side with metal ion concentration that is higher. So it goes from lower to higher concentration. The reason that is so it leaves the cell that has a lower concentration, so that side will be oxidized. Remember, where it's oxidized, those metal atoms come off as ions, and so the ion concentration in that half cell will increase. And on the other side, where the electrons are going, you'll have reduction taking place, and you will have your concentration of ions in there decreasing. And so that'll go until the two concentrations are the same. Let's look at an example here. So over here on the left, we have a standard cell where both the copper 2 plus solutions on both sides are 1 molar. We have copper metal there. And here we see a voltage of 0 volts. So there are no electrons moving back and forth. There's no reason for them to, since both half cells are identical. Over here on the right, we actually have a voltage of 0.068. So it's not exactly going to drive an e-car anywhere, but it does produce a voltage. Notice I've got slightly darker blue solution here indicating a higher copper concentration. So electrons are going to come out of the anode and they're going to come down into here. And so I'm going to have copper concentration increasing because copper atoms are going to be oxidized, giving me more copper ions right here. So my solution becomes more concentrated. And then here I'm going to have copper ions coming out of solution and being deposited as copper metal, and that's going to reduce the concentration because I have a reducing reaction going on here. And so that will go until those concentrations are the same. Now, how did we get that 0.068 volts? Well, we just apply our Nernst equation. Now, for a concentration cell, my E0 cell is 0 because that's the voltage rather under standard conditions. And so we have there that that's 0 minus, and here we use the common log form, so 0.0592 over 2 log of 0.01 over 2. If I add these two equations together, we would have to make sure we note which is the reactant and which is the product. We see that the copper ion solution here that's low is the product, so the 0.01, and the one that's higher would be in the reactant, and so that's down here, R2. And when we carry out that calculation, we get a 0.068. So it really is just kind of a neat little thing there, a neat side effect of the Nernst equation.